Okay, into our final subtopic of the managing chemical processes topic, and we're going to look at optimizing production. And in particular, we're going to look at flowcharts, which is an important thing we need to understand for this course, as well as looking at what we've learned about rates and equilibrium to optimize production in chemical industry. Let's get into it. Okay, so let's just go with what's here. Designing chemical synthesis processes involves constructing reaction pathways that may include more than one chemical reaction. So if you're going to set up a chemical plant to make, whether it's to process ore as the one we're going to talk about, or to make some chemicals that are really important, or to process crude oil to make lots of different things, you're going to have lots of potential different chemical reactions that you need to include. The steps in industrial chemical processes can be conveniently displayed in flowcharts. And what you need to be able to do is interpret flowcharts and use them for purposes such as identifying raw materials, chemicals present at different steps in the process, waste products and byproducts. So let's have a look at this. Firstly, a flowchart is a diagram representing the various stages of an industrial process. Might need to make that a little thicker there. Let's go with that one. And basically, this whole thing here is a flowchart. That should be fairly obvious. Raw materials are unprocessed starting materials. So unprocessed starting materials used in chemical processes, e.g. metal, ore, natural gas, crude oil. So if we look at this one, we have some sulfide ore coming in here. That would be one example of a raw material. We also have some air coming in here. That's a raw material. It's used in an unprocessed form. There is other things that go into that, like oxygen and carbon and oxygen, but they are not in an unprocessed form, so we wouldn't necessarily call them raw materials. They are probably chemicals that are added at various points. The next thing that we need to be able to identify is the waste products. So these are unusable products produced in a chemical reaction. So that tends to be stuff like mine waste here, the mill tails that would go off to a tailings dam. Just trying to think. But yeah, waste, anything tailings tends to be waste. I'm looking to see there, but there doesn't seem to be any. Sometimes you would have like carbon dioxide being released. That might be one present. The other thing though, which are a little bit more useful, are byproducts. So these are usable products other than the target product that can be used in the process. So sulfur dioxide, if that's given off, can be used to make sulfuric acid, which is used or part of the process in copper or zinc processing. So here in this case, sulfuric acid gets produced as a byproduct, and then we can see doesn't show where the sulfuric acid goes back in. It's not the best flowchart in the world. We'll talk about an acid plant here. But often, we have products that get used which aren't the intended product but may still well be useful and have a use. That's what we refer to as a byproduct. So there you go. That's a little bit of an overview of what a flowchart is and how you sort of go about interpreting what's going on within one of them. It's really just common sense. I think if you're familiar with what they are, it'll come together fairly quickly. So let's get on and talk about optimizing production. So industrial processes are designed to maximize profit and to minimize impact on the environment. At least we hope they're designed to minimize impact on the environment. Explain how certain reaction conditions represent a compromise that will give maximum yield in a short time. Explain the impact of increases in temperature and pressure on manufacturing costs and costs in manufacturing conditions and costs and on the environment. Explain the use of a catalyst may benefit both the manufacturer and the environment. So let's take a typical process, the Haber process. It's an important industry reaction to make ammonia that's then used to make fertilizers, explosives, refrigerants, and lots of other things. So we give that by the reaction here. Nitrogen plus hydrogen gas goes to ammonia, NH3, and it's an exothermic process. It gives off heat. So let's think about if we increase the temperature of this reaction. Well, if we increase the temperature, the rate will increase because we'll get more productive collisions. Yay, that's good. We want to make this stuff faster. We want a faster rate. That's good. However, the yield will decrease because it's an exothermic reaction, so it gives off heat. If you heat it up, the reverse reaction will be favoured, going back to the products going back to the reactants rather than the product ammonia, so we will get less products. So then we will get a lower yield. The yield will decrease because the reverse reaction is favoured due to Le Chatelier's principle that we talked about in the last subtopic. So we have two competing effects here. And what a chemical engineer would need to do is basically come up with a balance. So find out at what point will I get not too slow a rate, but a good enough yield. I don't want to go to a super high rate, but have a very low yield. I don't want to have a very, very high yield, but a very, very, very slow reaction. So it's about balance. They could also think about increasing pressure. If we increase pressure, the rate will increase because there'll be more productive collisions between the nitrogen and the hydrogen. So that's good. Also, the yield will increase because we have 1 nitrogen, 3 hydrogen, 4 molecules here, 2 product. If we increase pressure, it will try to decrease pressure, form less molecules, so you'd favour products. So you might think, yep, let's increase the pressure. Higher the pressure, the faster, the more yield. Sounds really good. Why not super high pressure? Well, we come into this next point here now. Temperature and pressure require energy. The problem with energy, firstly, it costs money. For all the energy, you've got to buy your energy somehow, whether it's by buying electricity or buying fuel to provide the energy, whether it's to increase the temperature or increase the pressure. So at some point, it just doesn't become economic. It's not profitable to have a pressure so high that it would cost so much money that it wouldn't make it worthwhile. Also, the problem with using lots of energy is often that's going to result in CO2 emissions, which can contribute to global warming and all those sort of things. So that's why we have to be a little bit careful about going to too extreme conditions, even if they will help both the rate and the yield. Finally, catalysts can increase the rate for the same energy input. So with a reaction like this, catalyst won't change the yield. The yield is determined by the equilibrium constant. It's not affected by a catalyst. It's not affected by how fast you get there. However, you can put less energy in and get the same amount of products quicker. So that's the advantage of using a catalyst. It will increase the rate for the same energy input, i.e. you will increase the speed that you make your products without needing any additional energy needs or energy costs. So I think I've said that there. A catalyst does not affect the theoretical yield, the Kc value though, only the rate. But it's still an advantage if you can make it quicker with less energy. That can obviously increase your ability to make a profit out of the process. So that's it for optimizing production, and that is also it for managing chemical processes. Thanks for watching.